Hello, Mr. Betts here. I want to take a look at a few examples that use integration by parts. So some indefinite integrals mixed in with with a definite integral to make sure that we know what our work's going to look like for that. So I'm going to make my choices here for u and dv so that when I take the derivative of u, it gets simpler, and when I take the antiderivative of dv, it does not get more complicated. So this one is about as straightforward as those choices get. U is going to be x, and dv is going to be e to the negative x times dx. So then we take the derivative of u, and we take the antiderivative of dv, and we plug into the formula. So we're going to get u times v is going to be negative x times e to the negative x times minus the integral of v du. Now v has a negative here, so that's going to make that a plus, and then it's going to be e to the negative x dx. So now we want to evaluate this antiderivative here. So we keep the first part of the expression the same. Antiderivative of e to the negative x is e to the negative x times negative 1, so minus e to the negative x plus c, and there's your answer. In this example, I'm going to go through this one two different ways. The first way, I'm going to use integration by parts, just like normal. And we get that. So using the formula for integration by parts, we're going to have negative 1/2 x squared times cosine of 2x minus the antiderivative of negative 1/2 2x is going to cancel out. X times cosine of 2x dx. Now, we still have a product, so we are going to have to do integration by parts again. And this repeated use of integration by parts should hopefully have you thinking that tabular integration might be a good option, which is the second way that I'm going to do this problem. Oops. It's going to be positive 1/2 sine of 2x. So this is going to equal negative 1/2 x squared cosine of 2x. And then for this expression, we're going to have u times v. So it's going to be plus 1/2 x sine of 2x minus the antiderivative of v du. And now we have an antiderivative expression that we can evaluate. So again, the first part's going to stay the same. And then the antiderivative of sine is negative cosine. And the 1/2 is going to be multiplied by 1/2 because of the chain rule there. Long, complicated expression, but that should be the correct answer. Now, with repeated use of integration by parts, tabular integration tends to be a lot easier. So let's look at how that would work with this example. So we're going to choose u is going to be x squared still, and dv is going to be sine of 2x. So in the u column, we're going to take derivatives until we get to 0. And then in the dv column, we're going to take antiderivatives until we get to that 0. Now we're going to multiply along diagonals. First one's going to keep the same sign. The second one's going to change. The third one's going to keep the same sign. So first term, we have x squared times negative 1/2 cosine of 2x. So it's going to be negative 1/2 x squared cosine of 2x. And then we're going to have the negatives cancel, 2 and the 1/4 cancel, so we get 1/2, so plus 1/2 x sine of 2x. And then the last one, the 2 and the 1/8, they're going to do some reducing, and we get plus 1/4 cosine of 2x plus c. So with tabular integration, this chart right here organizes all of our work, and we're able to go straight to our answer, which is the same answer we got the other way, but a lot more quickly. Now, if we do the same thing, but it's a definite integral, we want to make sure that we do our work appropriately. And I would definitely use integration by parts. I'm sorry, I would definitely use tabular integration for this particular example. So let me recreate that really quickly here. So we need an antiderivative for our definite integral. So the antiderivative will be negative 1/2 x squared cosine of 2x plus 1/2 x sine of 2x, and then plus 1/4 cosine of 2x. And then instead of the plus c, remember with a definite integral, we are just evaluating this expression from 0 to pi over 2. I say just evaluating. It's not necessarily a simple thing, but it's a straightforward thing. So we're going to plug in the pi over 2 first. So negative 1/2 pi over 2 squared cosine of pi over 2 times 2 is cosine of pi, plus 1/2 times pi over 2 times the sine of pi. And then plus 1/4 cosine of pi. Then we're going to subtract what we get when we plug in 0. When we plug in 0, the term with the x and the term with the x squared and the x are both going to go away. So the only one we're going to end up with is the 1/4 cosine of 0. And we should evaluate these expressions. So cosine of pi, sine of pi, cosine of pi, cosine of 0, we should do those. Sine of pi is 0, so that term's going to go away. Cosine of pi is 1, so this first term here is going to be negative pi squared over 8. And then we're going to have cosine of pi is 1, so plus 1/4. And then cosine of pi is 1, so minus 1/4. So those 1/4 cancel each other out, and we just get negative pi squared over 8. Okay, last example. This one is definitely going to be a tabular integration problem. With this x cubed here, when we take the derivative, we're going to get 3x squared. So this is one where we're actually going to have to do integration by parts 3 times if we were going to do integration by parts. So tabular is a good choice here. So u is going to be x cubed. dv is going to be e to the 2x. And we take derivatives and antiderivatives. And we multiply along diagonals. First one keeps the same sign. Next one's going to change. Next one's going to stay the same. Next one's going to change. I do want to point out that every term is going to have an e to the 2x in it. So I'm actually going to start my expression with an e to the 2x factored out. And then I'm going to just include in the parentheses everything that's left. So it's going to be x cubed times 1/2. So x cubed over 2. We're going to have 3x squared times 1/4. So, and that's minus. So minus 3x squared over 4. Then we're going to have 6x times 1/8. So it's going to be plus 3x over 4. And then we're going to have minus 6 times 1/16. So minus 3/8. And then plus c at the end. And that's it.